Hello, so this video is quickly going to go over the differences between digital and analog components, hopefully give you some examples of each, show you them in circuits and leave you with an understanding of what the graphs of voltage versus time would look like for a digital or analog component. So to kick us off, I've got some pictures of things that you might have sort of associated with digital and analog before. An analog clock you've probably all heard of with the traditional hands that move around, and then a digital clock, and we'll talk a little bit why about each of those is considered what they are at the end of this. The easiest way to sum this up is I like to think about light switches. The dimmer switch, the one you turn and can vary the brightness of your lights in your house, that would be considered an analog component, and the simple flick on and off switch, toggle switch, would be considered a digital component. So anyway, let's talk about digital components first. This is the basic fact. They can only be in one of two states. They're either on or they're off. Like the light switch here, it's either pressed and the lights are on, or it's pressed in the other position and the lights are off. It can't be anywhere in between. So they have two states. Now those words, high, low, on or off, 1 or 0, you might hear referred to at different times and in different contexts. They all mean the same thing. What we're actually talking about here is voltage. High or low means there is a voltage there or there isn't. In the case of our light, if the voltage is there, the light's on. If the voltage isn't there, current doesn't flow and the lights are off. So, all of these components, pretty much any switch in electronics, push to make, push to break, single pole, single throw, double pole, double throw, reed switches, and there are others out there, are all digital components. They're either in one position or the other. Some you have to hold down, some stay latched, but it doesn't matter, they only have two possible states. Later on in the course we're going to look at microcontrollers, and you can buy all sorts of modules on eBay now. You can get PIR sensors that they're kind of like the room alarm sensors that sit in the corner and scan a room, clap sensors. We might talk about infrared beam breaks, you know, for protecting a doorway or something. These all behave digitally as well, or they give a digital output when they detect something. So in the case of the clap sensor, when you clap your hands, it will give out a high voltage every time the clap is above a certain volume level. Okay, so some components mix it up a little bit and actually have analog things in them but give you a digital output, but we'll talk about them later in the course. All of these devices here, logic gates, microcontrollers, sorry about the spelling mistake, all modern computer processors and thyristors, they're all digital devices. Although they're a lot more complicated than switches, essentially they're all built around these things called transistors, and transistors in electronics we think of them as either being on or off, and this is why they're digital. So any system, so this goes for computers, that uses binary, and you may or may not have heard of binary before, but any that use binary information, which is basically a string of ones and zeros, are considered digital. Now binary, if you've never heard of it before, we're going to look at it very, very quickly because it's important, and then we'll look at it in action. We'll look at some digital components. Binary is just a way a computer understands real life, if that makes any sense at all. Computers don't have a brain like you and I. They only know one of two things. They can either measure if something's on or measure if something's off. So when something is on in electronics, that means a voltage is flowing. We represent this in computing by the number 1. When something's turned off, we represent it by the number 0. This is why I haven't got an image to show you. In fact, let's just Google it. Just because it helped. I didn't realise this until years ago. If you Google the power symbol that you find on any device for turning it on and off, what have you got? A 1 and a 0. There we go. That shows it quite nicely. So it comes from this concept of binary. So anyway, this is important because it's how we send information to computers. So you can send basically a load of on and off pulses to a computer, and it will understand them. And it does this because a computer can't count like we do as humans. It can't count above 2, actually. It does all its maths using zeros and ones. Now that'll melt your head at first until you look at it like this. If the computer got this set of numbers in that sequence, 00110110, it would understand it as the number that me and you know as 54. And the reason for that is the computer assigns a value to each number in the column. I don't want to spend too long on this, but basically any column that is on is added together. So we've got a 1 under 2, a 1 under 4, a 1 under 16, and a 1 under 32. If you add 2, 4, 16, and 32, you get 54. Right, and obviously you can imagine any combination of these, ones, zeros, ones and zeros, will produce different combinations of numbers. So that's basically how a computer does it. The reason I'm waffling on about this and boring you is because, going back to digital components, they are just a voltage, on or off, there or not there. And therefore, that all translates to this. Computers are going nothing, nothing, something, something, nothing, something, something, nothing. And it will translate that into numbers and data, and this is what makes computers and how I'm talking to you over the internet from miles away possible. But it's a lot more complicated than that in reality. Alright, so anyway, digital components, let's look at some, as I'm managing to make this video longer than it should be. Alright, here's a simple circuit. This is an example of a digital circuit. I have a digital input, my push to make switch, and that switch can either be, I'll just turn the graph off quickly, that switch can either be pressed and the motor will spin in this case because I'm turning on the transistor, or it can be not pressed and the motor will not be spinning. Nice and easy, on or off. There's no halfway, there's no middle speed, it's either on or it's off. That is the two states I was talking about here, on or off. To prove it, if I look at voltage levels, so if I put a voltmeter here, and measure the voltage I'm getting into my transistor, no volts or 5 volts, no volts or 5 volts, 0 or 1, low or high. Okay, Circuit Wizard lets me look at logic levels as well. So I can see at the moment I've got 0 going into my transistor, which is what powers my motor. Press the switch and it changes to a 1. So there we go, 1 or 0, 1 or 0. Now the last thing you need to know for your smart product design course is what the graph of this would look like. You need to be able to describe the graph for a digital signal. So what I've done here is I've put a graph in Circuit Wizard. It's already given the game away, but I've put a probe here that's measuring the voltage. This is time along the bottom, voltage here. If I press play, you'll see that I press the switch, it's high, let go of the switch, it's low. It's either up or it's down. It's nowhere in between. It's never half up or half down. The only thing that can change is the width of these, okay? So the way I like to remember this is it looks like castle turrets. That's what a digital signal looks like. Again, it's either on or it's off. Hope that's stuck in your brains. That goes for this component as well. Alright, I could swap that out. I could get my latching single pole double throw switch, stick it in, and that is also going to behave digitally. It's either on or it's off. The only difference with this type of switch is I don't have to hold it down to achieve that. Okay, this is pretty much what your light switch in your house is. Right, on to analog components. Back to the boring PowerPoint. So these guys, they have an infinite range of states or values between a minimum and a maximum. And when I say infinite, I mean infinite. In theory, there is no definite level they can be at. It could be anywhere between a minimum and a max. And when I say state, we're just talking about the amount of voltage that's present at that moment in time. It could be half a volt, 1 volt, 1.11, 1245 volts, 2.3 volts. Could be anywhere between a minimum voltage, normally 0, and a maximum voltage, like typically 5 volts in modern electronics. So some example analog inputs are all of these: light sensors, light-dependent resistors, thermistors, variable resistors, and potentiometers. These guys are the same thing, by the way. A moisture sensor circuit, phototransistors. You may know that you can use a motor in reverse. I.e., if you spin the shaft of a motor, it generates a voltage. That would be analog. Hall effect sensor is a type of magnetic sensor that, when you move a magnet past a coil of wire, will create a voltage. All of those are analog, as in it varies on many factors. Old school electronic chips, so you won't know about them on your course, but people on YouTube might care. So 555 timers, op amps, other older integrated circuits are considered analog because they deal with different voltage levels and can handle all voltage levels as inputs rather than on or off. Transistors, frustratingly, actually are analog devices, but we treat them in electronics and computing as being digital because generally we only care if they're on or off. So I wouldn't, if you're doing your homework for me in smart product design, I probably wouldn't bother talking about transistors, because it depends who's reading it at the other end as to how they interpret whether they're digital or analog. I would talk about these guys up here as surefire bets, not the others. You may have heard, if you're old enough, that TV and radio changed to DAB, digital TV, digital radio, and everyone had to go out and buy new tellies and new antennas and stuff. All it meant was, in the old days, analog signals used to be sent by varying, I guess, the strength or the frequency of a radio wave, which got turned into a varying voltage, and that's why they were called analog. Nowadays, if you could look at the radio signal, it would just be a packet of information, ons and offs, highs and low pulses. So I guess, real simply, the graph, if you looked at your TV's information coming through the aerial, it would be lots of ups, downs, ups, downs, ups, downs, just of different widths and at different times apart. In the old days, the voltage or the radio would have been up and down and all over the place and varying. Okay, so that leads us on to the analog components. We're nearly done. You can go and have a cup of tea in a minute. So if I put an LDR in, which I know is an analog device, press play, what we will see if we look at the voltage is, in darkness, nothing, and then if I make it slightly bright, I get a bit of a voltage here, a bit higher, a bit higher, a bit higher. I'm just going to change this actually to make the effect more obvious. There we go. Okay, what I might actually do is fit to data, that's better, so you can see it better. So as you can see, my graph can be at a whole bunch of different levels, between a minimum and maximum. And when I've described this to students in the past, they've said, yeah, it looks a bit like a heart rate monitor in a hospital, or maybe like mountain ranges, or if you're recording sound into a computer, like you see this kind of waveform effect. Right, so the point is, it could vary over time. And what that means in my circuit is I can create a situation where, look, the motor is sort of turning very slowly, so it's partly on, or if I make it a bit brighter, the motor turns a lot faster, or super fast, or somewhere in the middle. Alright, and that's the point of an analog signal. It completely varies. So that's pretty much it. The only last thing I want to talk about, which is a mild point of interest, old school audio. So like, if you're not old enough, anyone really, to remember vinyl records when they first came out, they are all analog, as in the sound is recorded directly and represents exactly what it is. Modern sound is recorded digitally, which means these ups and downs get turned into a graph a bit like that, I suppose, but at different heights, and technically you're going to lose information when you do that. So you won't notice a difference, nobody notices a difference, but there are some audio nerds on the internet who will tell you they can hear the difference between an analog record and a digital record because they can detect the missing quality. I think it's all rubbish, but it's just something to consider. Alright, so anyway, that's 13 minutes. It's probably a bit too long for this, but there's your summary. That's what it means. These are the components, these are the graphs, that's analog. The binary bit you don't need to know for your course, but you do need to know 1 means high and 0 means off, but it just helps to know what the rest of these mean. So if it ever comes up in a future thing, it might make some more sense to you. Alright, thank you very much.